As you can remember, on our previous lecture, we have learned capacitance of three different types of capacitors, and they were parallel plate capacitor, cylindrical capacitor, and spherical capacitor. And now it is necessary to say that there are different types. There are two main types of connections of capacitor. And the first type is connection in parallel. Connection in parallel. What does this mean? Connection in parallel. Connection in parallel. I will draw just two capacitors, but this result can be extended for any number of capacitors. So what is connection in parallel? If we have two capacitors, and here and this. These two parallel lines means capacitor on a scheme of electric circuit. Oh, and here is the second capacitor, and they are connected. They are connected in parallel. So this is two capacitors. Two capacitors connected in parallel. Two capacitors connected in parallel. Two capacitors connected in parallel. And okay, and the first capacitor has capacitance C1. And the second has capacitance C2. And the question is how to calculate capacitance of this system. So let's try to do this. And let's consider that here we have electrostatic potential Phi1. And here we have electrostatic potential Phi2. Electrostatic potential Phi2. Phi2. And it means that the potential difference is U. Potential difference is U, and often it is written as V it is often written as V, because potential difference and voltage is the same. This is the same thing. So U potential difference is equal to phi1 minus phi2, phi1 minus phi2. But as we can see, if you look at this carefully, we can see that this part of the system, which is surrounded with blue line, this part of the system is the same conductor, and it means that its surface is equipotential surface, and as we can remember from electrostatic, this surface has the same potential in every point of its point. The potential is the same. The potential is the same in every point of this surface. So it means that for first capacitor we can write potential difference will be the same phi1 minus phi2, because left plate of this capacitor has potential phi1, and the second will have potential phi2, because we can notice that right plates of both capacitors and they are part of the same conductor. Right and left, right plates of both capacitors are the part of the same conductor. So it means that for both capacitors we have the same potential difference, phi1 minus phi2, phi1 minus phi2. So from here we can make a conclusion. That that for connection in parallel, we have that potential difference for first capacitor is equal to the potential difference of the second capacitor, and it is equal to the potential difference of the whole system. And it can be written phi 1 minus phi 2, phi1 minus phi2, potential difference. Okay, do you have any questions about this? No question. No questions. Okay, if there are no questions, let's clean some unnecessary information from the screen, and I think connection. I will write a connection of capacitors. Connection of capacitors in parallel. Connection of capacitors in parallel. This equation we have for potential difference. And what about electric charge? What about electric charge? What about electric charge? Here we have U1, and here we have U2. And what about potential? Or what about electric charge? What about electric charge? Let's imagine that when we charge our system, it takes charge Q, and the part of this charge Q1 will go to first capacitor, Q1, and the second part will go to the second capacitor. The second part of charge Q will go to the second capacitor. But according to the law of conservation of charge, we will have that charge Q is equal to Q1 plus Q2 plus Q2. It is the result of charge. It's the result of law of conservation of electric charge. Because electric charge cannot appear from nothing, and it cannot disappear into nothing. It is according to the law of conservation of electric charge. Okay, so here we have Q1, and here we have Q2, and here we have Q2, and here we have Q2. Law of conservation of electric charge. Law of conservation of electric charge. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, let's continue. Let's continue. From one of our previous lectures, I think you can remember that electric charge of capacitor is connected to its potential difference and capacitance. This is connected via formula. Q is equal to capacitance multiplied by potential difference, multiplied by the potential difference, and we can write a similar formula for charge Q1. It will be C1 multiplied by U1. But according to this, we have that it will be C1 multiplied by U. And for second charge, we have very similar thing, very similar formula, that it will be C2U2, and this is equal to second capacitance multiplied by voltage. Okay, and from here we have that we have that Cu is equal to C1 first capacitance multiplied by potential difference, and it oh, no equal, it is plus, it must be plus C2 multiplied by U. Okay, and this equation must be true at any meaning of U, and it means that we can rewrite this equation without potential difference. So it gives C1 plus C2 plus C2. Okay, do you have any questions? About connection of capacitors in parallel? No questions. No questions. Okay, if there are no questions, I will hide some unnecessary things. And just leave something that is necessary. Something that is necessary for the future. Something that is necessary for our future education. Okay, and I will draw a red frame around this. I'll draw a red frame. So here we have different. Here we have formula for connection of capacitors and in parallel. And the second important type of connection of capacitors is the connection in series. Connection in series. Okay, let's have a look at this. Connection of capacitors in series. Connection of capacitors in series. Connection of capacitors in series. And let's draw this. So if we have connection in series, it will be such system. It will be such system. A first capacitor, and it will be drawn as two parallel lines, two small parallel lines mean a capacitor. Capacitor on a scheme of electric circuit. And here is connection between them, and okay, this is a connection in series. Connection of capacitors in series, and the capacitances of them are known. The first capacitance is C1, and the second capacitance is C2. The second capacitance is C2. And okay, what can we say? What can we say about potential difference? About potential difference. We have here we have electrostatic potential Phi1. Here we have electrostatic potential Phi2. But we also have the third conductor, because first conductor is here. It has potential P1. The second conductor is here. This is the second conductor. And we also have the third conductor between first and second. This is the third conductor. And it has its own electrostatic potential that we will assign as phi 1 and 2. P1, 2. So it will be the third conductor. The third conductor. Okay, and what about potential difference? What about potential difference? Now we have that potential difference of first capacitor. It will be U1 is equal to phi 1 minus phi 1 2. And it is here. Here we have U1. Here we have U second, and U second 2 is equal to phi 1 2 minus phi 2 and the potential difference for the whole system will be U and it is equal to phi 1 minus phi 2 minus phi 2. Okay, and what do we have from here? From here we have that if we add U1 and U2, if we calculate this sum plus U2, it will give us this. It will give us this plus here we will have that it is equal to this and it is easy to understand that it will be phi 1 minus phi 2 but this is equal to electrostatic it is equal to potential difference of the whole system, potential difference of this connection in series, in series. Okay, do you have any questions about this? No questions. Okay, if there are no questions, we can write the summary that we can summarize that we have obtained U1 plus U2 U1 plus U2 1 plus U2 U1 plus U2. Okay, this is potential difference. This is potential difference for connection of capacitors in series. Okay, and what about electric charge? What about electric charge? Okay, let's try. I will redraw this system, and I just noticed that first capacitor has charge Q1, and the second capacitor has charge Q2. Has charge Q2. Okay, and what do we have if we try to charge this system? I will remove some letters. If we try to charge this system, okay, let's do this. Let's give the charge Q to this system. If we do this, the left plate of first capacitor will obtain the charge plus Q. Charge plus Q. And of course, the second plate, the right plate, will obtain the charge with the same absolute value, but with another sign. Will be minus Q. Will be minus Q. But we know that left plate, but the right plate of first capacitor and the left plate of second capacitor are the same conductor. So this is the same conductor. And if we have a charge minus Q on the left side of this conductor, we of course will have charge plus Q on right side of this conductor. But right side of this conductor is the left plate of second capacitor. And so here we have again charge minus Q. So what does this mean? It means that the charges of both capacitors will be the same. So for connection in series, we have that charge that Q1 is equal to Q2, and this is equal to Q, charge of the whole system. Charge of the whole system. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, if there are no questions, let's calculate the capacitance. Let's calculate the capacitance of this connection. Let's calculate the capacitance from this formula. As you can remember from electrostatics, from one of our previous lectures, we have that charge Q, charge of capacitor, is equal to its capacitance multiplied by its potential difference. And from here we can obtain that potential difference for capacitor, potential difference of capacitor is equal to its charge divided by its capacitance. But very similar thing we can do for the first capacitor, for capacitor C1. So for first capacitor we have U1 and C1, and this is equal. This will be equal as we remember the equality between charges. As we remember this, we can make a conclusion that it will be Q divided by C1. Q divided by C1. This will be Q divided by C1. Divided by C1. Okay, and the same thing we have for the second capacitor. For the second capacitor, but it is necessary to remove lower index 1 and left upper and left and to right lower index 2. And to right lower index 2. Okay, and what do we have? What do we have here? From this, and from this and this, we will obtain that Q divided by C is equal to Q divided by C1 plus Q divided by C2 divided by C2 divided by C2. Okay, and from here, because this equation will be true for any charge Q. This equation must be true for any charge Q. We will obtain that it is equal to 1 divided by C plus 1. Oh, sorry, it's not plus, it is equal. It is equal to 1 divided by C1 plus 1 divided by C2. 1 divided by C2. Okay, what questions do you have about this? No questions. No questions. Okay, if there are no questions, I will clean some things from the screen. I will clean this from the screen, and I will just leave this. I will just leave this. And for connection capacitors in connection of capacitors in series, we have obtained such formula. Okay, what questions do you have about this? What questions do you have about it? No questions. Okay, great. That's great. I hope everything is clear. And let's go. Let's continue. Uh, let's go to the next question to learn. The next question is will be the next version will be that how to calculate energy of system of electric charges. Energy of system of electric charges. Because if electric charges are fixed, if they cannot change their positions, if they don't move, they will produce electrostatic field. And as you know from electrostatics, electrostatic field is always a potential field. Is always potential field, and this means that we can consider and we can define potential energy for system of fixed point electric charges. But how to calculate this potential energy? To do this, let's calculate the work of producing of system of electric charges. Let's calculate this work, and let's do this step by step. Let's produce a system of electric charges step by step. So let's bring from some infinitely from some point that is infinitely far from us. Let's bring electric charge Q1 from infinitely distant point. So let's do this. Let's bring this electric charge Q1. Do we need to make work against electrostatic force when we are bringing this charge? We don't have to do any work against electrostatic field, because if there are no charges, there are no electrostatic field. And before we bring charge Q1, there wasn't any electrostatic field. So potential energy of one charge will be equal to 0. It will be equal to 0. Potential energy of one charge will be equal to 0. It will be equal to 0. Okay, and what about potential energy? What about potential energy of two charges? So let's bring the second charge. Let's bring the second charge, Q2. Let's bring the second charge Q2. And the distance between them will be R, R1, 2, 1, 2. This distance will be R1, 2, distance from these charges. And how to calculate how to calculate work that we have to do that we have to do to bring the second charge uh, we can calculate this from electrostatics. So potential energy of two charges is equal to it is equal to uh, it is equal to minus work that is necessary to bring charge Q2 from infinity to its position to this point so it can be calculated as minus Q2 multiplied by P electrostatic potential in infinitely in infinity and minus electrostatic potential of charge Q1 in point where charge Q2 is present, where charge Q2 is present. So Phi2 is electrostatic potential of charge Q1 in point where charge Q2 is present. So okay, and as you can remember, we can choose the origin of electrostatic potential. So we can choose electrostatic potential in infinity, and the best way to choose this is to make it equal to zero. And so we have that it will be Q2 multiplied by Phi2 it will be Q2 multiplied by Phi2 multiplied by Phi2 So this is potential energy of system of these two charges. And what can we say about potential Phi2? Potential Phi2 is electrostatic potential of charge Q1 in position of charge Q2. So it will be 1 divided by 4 P epsilon 0. 1 divided by 4 P epsilon 0. And Q1 divided by R1 2. So this will be charge. It will be charge potential Phi2. So from here we have that potential energy of this of two charges will be equal to Q1 Q2 and divided by R12. divided by R1, 2. Okay, do you have any questions about this? No questions. But it is necessary to notice that we can calculate this potential energy W2 in another way. We can bring we can for the first time we can bring charge Q2 and then bring charge Q1. So in this case we will have that it is equal to Q1 and Phi1. Q1 Phi1. And what is this? Phi1 is electrostatic potential of charge Q2 in position of charge Q1. So it will be Q2 divided by R. So it will be Phi1 R1 2. And of course here we have the same formula as it was before. Here we have the same formula. Here we have the same formula as it was before. Here we have the same formula. So from here we can write that. From here we can write. Maybe I will remove some. Things that we don't need anymore. I will remove them. And leave only necessary things. Leave only necessary things. Okay, so from here we can write that that potential energy of two electric charges is equal to Q1 P1, and this is equal to Q2 Phi2, Q2 and Phi2, Q2 and Phi2, and okay, and this is equal to this value. Okay, and it is useful to write this equation in some symmetrical form. It will be W2 is equal to 1 second, 1 divided by 2, Q1 Phi 1 plus Q2 and Phi 2. And it will be equal to this. It will be equal to this. Okay, do you have any questions? No questions. Okay, if there are no questions, okay, let's clean the screen. Let's clean the screen and let's clean the screen. And so for two charges, we have such formula. But in similar way we can prove, but I will not do this because of the lack of time. We can prove that for three charges we have Q1 Phi1 plus Q2 P2 and plus Q3 Phi Q3 and Phi3 and Phi3. Okay, and here we have 1 divided by 4 P epsilon 0, 4 P epsilon 0, here Q1, Q2 divided by R1, 2, plus Q1, Q3 divided by R1 and 3, and plus Q2 and Q3 divided by R divided by R divided by R and 1 and 2 3 R and 2 3. Okay, so do you have any questions about this? No questions. No questions. Okay, if there are no questions, let's we can also write this formula. We can also write this formula for any number of electric charges. Any number of electric charges. So it will be some WVN, and this will be equal to 1 second, 1 divided by 2, sum of E is equal to 1, from E is equal to 1 to N, and Q E and Phi E and Phi E, and this is equal to 1 this is equal to 1 divided by 1 divided by 4 P epsilon 0, 1 divided by 4 P epsilon 0, and here I is equal to 1 and 2N, and this here we have the second sum, that K is equal to I plus 1 and 2N. I plus 1 to N, and here And here we have Q, I, Q, K, and R, I, K. So it will be potential energy, potential energy, potential energy, energy of system of n point charges. Potential energy of a system of n point charges. Of n point charges. So it can be calculated. It can be calculated in this way. In this way. Okay. What questions do you have about this? What questions do you have about this? No questions. No questions. Okay. If there are no questions, let's calculate potential energy of charged conductor. Let's calculate potential energy of charged conductor. So let's use this formula for endpoint charges to the potential energy of charged conductor. Charged conductor has the same charge in any part of its surface. So the surface of conductor is equipotential surface. So any point of this conductor has the same potential. And for some small part of surface of conductor, we can write this formula for some small part of surface of conductor. So we can write that d double v is differential of this energy is equal to phi potential of part of surface multiplied by its charge dq, multiplied by its charge dq, multiplied by its charge dq. Okay, and from here we can integrate this equation. To obtain energy of electrostatic field of charged conductor. So it will be the double V is equal to the integral from 0 to double V from 0 to double V and it will be equal to the integral from to the integral phi d u from 0 to q. From 0 to q. From 0 to q, but I have forgotten to write this 1 divided by 2. Of course, I have forgotten to write this. This is a mistake. It is necessary to fix. It is necessary to fix it. It is necessary to fix it because we have 1 second here. And we have 1 second here. We have 1 second here. And so, from here, what do we have? What do we have? How to calculate this integral? It is necessary to remember that the surface of conductor is equipotential surface. So any point of the conductor has the same potential. So electrostatic potential phi doesn't depend on this, doesn't depend on dq. It means that phi may be written outside of the integral. So we can write this from 0 to q and dq with this. And this integral is easy to calculate. So it will be just phi q divided by 2. Phi q divided by 2. Okay, do you have any questions about potential energy of a charged conductor? No questions. No questions. Okay, so we have we have uh, we have potential energy, potential energy of electrostatic field, static field of a charged conductor, of a charged conductor. Potential energy of electrostatic field of a charged conductor. It can be written as we have proved. It can be written with this formula. But it can also be written in some other way. We can remember that charge Q, charge of charged conductor, is equal to its capacitance multiplied by electrostatic potential on its surface. So after substitution, we'll obtain C squared P divided by 2. And after and we can also write that electrostatic potential is equal to Q divided by capacitance. So from here we have that it is equal to Q to the power of 2 divided by 2 multiplied by capacitance. Okay, what questions do you have about this? No questions. No questions. Okay, if there are no questions, let's clean this. And let's write a red frame around this. let's frame this in red. Potential energy of electrostatic field of a charged conductor. Of a charged conductor. Of a charged conductor. Of a charged conductor. Okay, and let's write this potential energy for capacitor. Let's calculate potential energy of capacitor. How to do this? How to do this? As you know, capacitor consists of two conductors, with the same charges that has the same absolute value but different signs. So potential energy, we can write potential energy of electrostatic field inside a capacitor. Inside a capacitor. Electrostatic field inside a capacitor. How to calculate this? Because a capacitor consists of two conductors, so its potential energy will be energy of these two conductors. So first conductor has charge Q and potential Phi1, and the plus energy of second conductor, and this will be charge minus Q and divided by 2. Okay, and from here we have that it will be Q divided by 2, Q divided by 2, Q divided by 2, and here we have that Phi1 minus Phi2. But you know that Phi1 minus Phi2 is a potential difference. So it will be Q multiplied by potential difference divided by 2. It will be Q multiplied by potential difference divided by 2. Okay, do you have any questions about this? No questions. Okay, that's great. So in this way, we have obtained a formula for potential energy of electrostatic field inside a capacitor. And of course, for capacitor we have that its charge is equal to its capacitance multiplied by potential difference. So this formula can be written in another way. C squared U divided by 2. And of course, we can rewrite this formula as U is equal to Q divided by C. Q divided by C and it will be it will be Q to the power of 2 divided by 2C. Divided by 2C. Divided by 2C. Okay, what questions do you have from here? No questions. No questions. Okay, if there are no questions, let's frame this with red. Let's frame this with red. Okay, if you know this potential energy of electrostatic field inside the capacitor, we can use this. To calculate energy of any electric field. Calculate energy of any electric field. How to do this? How to do this? How to do this? To do this, let's remember what parallel plate capacitor is. So parallel plate capacitor has two parallel plates with charges plus Q and minus Q, plus Q and minus Q, and electrostatic plate separation. Plate separation is D. Distance between plates is a plate separation. It is D. And inside this parallel plate capacitor, we have electrostatic field. We have electrostatic field inside parallel plate capacitor. Inside the parallel plate capacitor, we have electrostatic field. We have electrostatic field. So it will be E. It will be E. Electrostatic field. And the area of each plate is equal to S. Okay, so energy of electrostatic field. Energy of electrostatic field inside this parallel plate capacitor is equal to double V. It will be double V C U to the power of 2 divided by 2. According to this formula. But from our previous lecture, we can remember that capacitance of parallel plate capacitor is equal to epsilon 0 S divided by plate separation. And the potential difference for parallel plate capacitor from our previous lesson is equal to absolute value of electric field intensity vector multiplied by plate separation. So from here we have that after substitution, we have that this will be 1 second epsilon 0 S divided by D and multiplied by E to the power of 2 D to the power of 2. to the power of 2. And this will be 1. Is necessary to simplify this. After simplifying, we will have that this is epsilon epsilon 0 e to the power of 2 divided by 2 and multiplied by s and d. But for a parallel plate capacitor, area of plate S multiplied by plate separation is equal to volume between plates. Is equal to volume between plates of this capacitor. For this capacitor. And the formula that we have obtained is true not only for parallel plate capacitor, but it is true for it is correct for any electrostatic and moreover for any electric field. It is true for any electric field. So we can just leave this. We can just leave this and for any electric field. For any electric field, we have that we have such formula. Okay, and what about but this formula was obtained for parallel plate capacitor, and electrostatic field inside it is homogeneous. But what to do is what to do in case if electric field is not homogeneous, in this case, it is necessary to consider infinitely small part of volume. So to generalize this formula, it is necessary to write it for differentials. It is necessary to write it for infinitely small part of volume. And this value is known as this value epsilon 0 e to the power of 2 divided by 2. This is energy density of electric field. So we can sign this as omega e, and it is equal to this. This is energy density of electric field. So from here we have that it will be omega e dV. And to calculate energy of electric field in some volume, it is necessary to integrate this equation. So it will give us a triple integral, because we have volume 3 coordinates x, y, z. So we have triple integral. Omega e dV. It will be triple integral, and in this case we have such formula. So for energy will be energy of electric field. Energy of electric field. Energy of electric field. It will be energy of electric field, and here energy density of electric field. But this energy density can be written in some other way. Let's remember that electric displacement vector is equal to epsilon 0. It is equal to epsilon 0, epsilon 0, e vector, and this can be written for isotropic dielectric. It can be written without for its absolute values. Can be written for its absolute values for isotropic dielectric. So from here we can rewrite this as d e divided by 2, and we can rewrite this as d to the power of 2 divided by 2 epsilon 0 to epsilon 0. Okay, what questions do you have about this? No questions. No questions. Okay, if there are no questions, if there are no questions, I will write that it is energy density of electric field. Energy density of electric field. This will be this omega E is energy density of electric field. Energy density of electric field. Okay, do you have any questions? If there are no questions, that's all for today. Thank you for your attention, and I hope to meet you next week. Have a good day.